Hello guys, how are you? Welcome to BT Core YouTube channel. In this video, we will talk about analysis of algorithms. So before we actually dive into analysis, we will talk about algorithm. Formally, what's an algorithm? What's the formal definition of algorithm? Before we go to analysis, we will talk about algorithm. What's an algorithm? Formally, an algorithm is a well-defined computational procedure, right? But let's speak about informally. An algorithm is a computational procedure which takes input, right? And does some computation on the input, and it returns output, right? So informally, this is what algorithm means. So now we will see analysis. So first of all, why do we need to analyze an algorithm? So the only reason is about the performance and results. Performance and results. So which means that always want our algorithm to perform well, and it should be well optimized, right? So that's why we need higher performance. So then, yeah, coming to next question, how? So this is why, and how do we analyze an algorithm? We will analyze algorithm with time and space complexity. So we will actually compute the time it's taking and also the space it's consuming. So these two factors are enough to analyze an algorithm, right? Yes. So now let's go to the time analysis. So when we say time, actually the time taken to execute the algorithm is actually depends on many factors. So let's say we run our algorithm on a machine A, so which has let's say 4 cores, and it's an i7 machine, and it's 16 gigs of RAM, right? And if you take the same algorithm, and let's say we run in a different machine, so let's say, but it has only 2 cores of processor, and it is, let's say, Pentium processor, and it has only 2 gigs of RAM. So if we compare the runtimes, so definitely they will be different. So in our analysis, we will actually ignore the kind of machine and all these constraints, and we will always assume that we are actually running our machine in an ideal machine, right? Ideal machine. So another assumption is, so the each statement in our algorithm will take a constant time, right? This is another assumption, right? These two are the assumptions we have to make before analyzing our algorithm. So now, coming to the next one, this is what we call as RAM model of computation, right? So this is what we call as RAM model of computation. Basically, when I say each statement will take constant time, so let me give an example. So, as I said, each statement will take constant time. So, can we actually assume this will take constant time? So, like C1? No, because uh, here internally, the because we are using the internal library, so this actually internal takes the sorting time. So in these cases, we should not assume that, right? So this is exception. But let's say when we have only return, let's say ARR, that's simple. So in this case, we can assume that it's taking the constant time. Now let's take another example. Let's say I have an array saying 1 2 3 4 5, and the element I want to find is 1. So in this case, how much cost this takes? Okay. So let's say this is the cost, and let's assume these are times, right? So for this, what's the cost? We can assume C1, and number of times the length of array. So in this case, we will assume uh, n is length of input array, Okay, right? So times is n, right? And if you take this one, so this statement will also take n times. And but this statement will actually take c3 time, but how many times is the question here. So we don't know how many times this because this actually depends on the element and also the array, right? So this is where we need to analyze. And if you see this c4, and this statement also will actually depends, right? See how does that depend. Let's say if our element is 1, so then how many, so if our element is 1, so we found our element in the starting, in the first element itself, right? So in that case what will happen is, so this will become 1, sorry, 1, and this will become 0, right? So in this case, what happened is, even this our for loop will actually take only one time, this also one time, c1 plus c2 plus c3, we can say this, right? So now now let's say our element is 3. Okay, so in this case let's analyze. The iteration will happen here and then here, and when it comes to here it will find it, right? So let's say 3 times, and this also 3 times, and this statement 1, and this 0. So now let's see this. So 3c1 plus 3c2 plus c3, right? So now let's say our element is, let's say 6. This actually runs for 5, because since our element is not found here, it will run for the whole array. And this also 5, but this will not even come, right? Because our element is not found. And this 1. So we can say it is 5c1 plus 5c2 plus c4. So can we write this as n, because our length is, we said n, and so when we do this, n into c1 plus c2 plus c4. So ignoring the constants, so we can say that our algorithm is taking at max n, right? So can we say this as our best case? So in the best case, our algorithm is taking, we can say this is a constant time. So in the average case we can say approximately log n times. And so in the worst case it's actually taking n times, right? In order to analyze this, so we need some notation to denote the running times, right? So those notation we will call it as asymptotic notations. So, and before that even, so can we actually make a graph, so where the x-axis will have input and this will have time, right? So let's see for the worst case. So as we are increasing our input, right, the time is linear, right? So something like this. And for the average case, so the time will be actually increasing and decreasing. And for the best case it is constant, right? Something constant like this. So this we call it as order of growth or rate of growth. Let's talk about the asymptotic notations. So what are those notations? So the first one is big O notation. So the first one is big O notation. So we will see what is big O notation. So this big O notation is nothing but the worst case. Let's say we have uh, an algorithm and we have the running times and the input size with us. So let's say this actually, when we plot it, let's say uh, we got the plot like this. Okay, so let's assume our algorithm as f of n. Okay, so now in big O notation we need to come up with a function g of n such that, so f of n should be less than or equal to c into g of n. So c is some constant greater than 0. Okay, now let's say we have a g of n, which if we plot it will came here. So let's we call it as g of n. Okay, so now if you see after some point, so which let's say n naught, after n naught we see that g of n is greater than f of n, right? So we say after n naught greater than 0, then what we can say is uh, f of n equal to big O of g of n, and also n should be greater than or equal to n naught. Let's take an example. We have our f of n, a linear function, so something like 9n plus 6, and now we need to take g of n, right? So let's start from g of n equal to n itself. Okay, so let's substitute in our formula. So 9n plus 6 should be less than or equal to some c into n, right? Now let's take c as 10. So based on our condition, so c should be greater than 0. So it can be any value. So I took it as 10, right? So now substitute that 9n plus 6 less than or equal to 10n, right? So now 6 greater than or equal to n, right? So that means for n greater than or equal to 6, c greater than or equal to 10, so our condition actually satisfied, which means that our f of n equal to big O of n. And also if you see this 6, which is our n naught. So here we see, right? So n naught, n greater than or equal to n naught. So here that n naught is 6. That means after the point 6, the g of n is asymptotically increasing by f of n. We might actually think that, so why not big of n? We can also say big of n square or big of n cube and so on will also satisfy the condition. But why we only take big of n? So we should always take the tightest bounds. Okay, so we must actually have to take the tightest bounds. That's why in our coding interviews mostly we will use big O notation only. There is one more notation which is theta notation. Similarly for big O, theta is average case. When we say our f of n equal to theta of g of n, then for f of n, when this condition satisfies, that means c1 into g of n less than or equal to f of n and less than or equal to c2 into g of n. So that means our f of n should be the tightest bound between g of n after some point, right? So we'll actually take an example here. Okay, so let's say our f of n is 5n square plus 9n plus 6. Now let's take g of n as n square. Now let's substitute in the formula. C1 into n square is less than or equal to 5n square plus 9n plus 6 and less than or equal to C2 into n square. Correct, right? Now let's divide by n square in all the sides. So we'll get 5 plus 9 by n plus 6 by n square less than or equal to C2. Now we need to take C1 and C2. So we already know that C1 comma C2 should be greater than 0 and n should be greater than or equal to n naught, right? So n naught should be greater than also 0, greater than 0. So that means after some point n naught. So now we will have to take the constant C1 and C2. Let's take n equal to 1. right? And C1 equal to let's say 2, and C2 equal to let's say 20. I think not 20, I think let's take 25. Okay, when we substitute 2 less than equal to, so when we substitute, what this will become 20, right? And then 25. Correct. So this satisfies the condition. So that means our f of n is the theta of g of n. In our case, g of n is n square. Correct, right? So where c1 equal to 2, c2 equal to 25, and n not equal to 1. So let's say if f of n equal to theta of g of n, so can we say f of n equal to big of g of n? Yeah, of course, of course. Why? Because if you see this part, only this part, see this we actually saw in the big O notation, right? See, it's the same thing. So that means we can see it, but the vice versa is not possible. The vice versa is not possible. Correct. Cool. So now let's come to omega notation. So this is, we call best case. We can call it as best case. Here you see f of n is less than or equal to c into g of n, and here the only condition remaining is c into g of n less than or equal to f of n, right? So yeah, our guess is right. So when we will say this is, there exists, so in f of n, where this condition is satisfied, c into g of n less than or equal to f of n for all n greater than or equal to n naught, c greater than 0, and n naught also greater than 0. So we'll actually not take an example for this because we already know it. So when f of n equal to theta of g of n, so when will this come true? So we can we say uh, f of n equal to theta of g of n if and only if f of n equal to big O of g of n and f of n equal to omega of g of n. Correct, right? Because whatever the conditions we have here was actually coming here. So then this condition comes true. Okay, so here is the graphs for all the three we have discussed. So this is for theta. So as we discussed, so you see f of n is the tightest bound between g of n, right? See, after n naught, correct. So we have constant c1 and c2, and this is big O. So after n naught, so g of n is asymptotically growing than f of n, right? And also omega. So omega is also obvious, right? So after n naught, g of n is asymptotically decreasing than f of n. Let's see this problem. So before I actually solve the problem, so I will recommend you guys to pause the video and try to solve by yourself. Yeah, so we'll actually go to the solution now. So here let's see what they are doing here. Okay, so they have actually initialized a and b, and then looping through looping n times, and then adding some random number to a, and similarly m times they're looping and then adding some random number to b. Good. As I said, so how many times uh, this is executing and the cost. Okay, so how many times this is executing? One time. So the cost is c1, and this one. So how many times this will? N times. That's the cost is c2. And this statement, since there is no condition, so that means this will execute for n times. So this, the cost is c3. Similarly, this m times, the cost is c4, and this also m times and c5. Cool. Now we got it. So let's sum all of these. So n into c2 plus n into c3 plus m into c4 plus m into c5, right? So so this is our function, right? So which is c1 plus n into c2 plus c3. I'm just simplifying it. So m into c4 plus c5. So this is our f of n. Now in order to tell the complexity, so in the big O notation, so as our method, we need to come up with g of n, right? What I can see is, because I have n and m, so I will say n plus m. Let's see. So when we have n plus m, so let's put it in our formula. So what is that? So f of n should be less than or equal to c into g of n, right? So we can obviously see one thing. Put c1 equal to 2 and c2, c3, c4 and c5 all as 2. Okay, so let's see that 2 plus n into 2 plus 2 is 4 plus m into 2 plus 2 is 4 less than or equal to c into our g of n is n plus m. So you can take any values, but for the simplicity I have taken all as 2, right? So now this will become 4n plus 4m plus 2 less than or equal to c into n plus m. I take c as 100. So when I take c as 100, obviously this will be greater, right? We can say our f of n, which is our program, which is our code, is big of n plus m. Simple. So instead of doing all this mathematics, we can actually come up with a simple tricks. So when we have this when we have this formula, the first trick is uh, drop all the lower order terms. Let's say here we have n. Let's say we have n square. Let's say we have n square and m square. So when we have that, so since n square and m square are the higher order terms, we should lower all the n. So n and m in that case. But in our case, the lower order is c1. So let's drop this, right? Then the second one is ignore all the constants. So we can simply ignore all the constants, right? So that means, so we can ignore these constants. So then simply we can write big of n plus m.